Thank you so much for the introduction, Nadja. Thank you for inviting me to speak here. Hello, everyone. So my talk is about anisotropic concrete. It's a material that is unidirectionally reinforced for extrusion-based concrete 3D printing, as it's suggested here. And I talk today on the behalf of my colleagues from École Nationale des Ponts et Chaussées, Building Innovation Lab, but also X3, which is one of our industrial partners. Let me say a few words about digital construction at the École Nationale des Ponts et Chaussées. So we are a public institution for training engineers and doing research. So we are concerned about material consumption and environmental impact of the construction industry. That's why we are working on robotics to automate, to improve quality, to have good quality control. We develop also on the right geometry for construction. So this is a large span wood structure where you have like much less steel connections. And at the middle, we do concrete 3D printing. So the background on concrete 3D printing has been really well explained. And I just wanted to make this allusion to my fellow German speaker here, but I don't speak German. So we have the cast-in-place concrete, which is kind of massive bow. We use massive amounts of material, and the process by itself brings this simplicity into bringing a lot of material right. But with the extrusion-based 3D printing, we are more into Flachenkonstruktion, and we are more, it is easier to do surfacic objects. It is easier and natural to do thin things, right? So we'll get back to that afterwards. And we want to have a reinforcement process that makes sense with this idea of surfacic objects. But how do we can reinforce extrusion-based concrete 3D printing? We'll get to the anisotropic concrete, but just the first background element. So we have printing reinforced concrete proposal here from TU Dresden, where they have a robotic system that allows assembling segments of reinforced concrete. We are approaches that are more at the scale of the printed laces, where you are nailing, stapling, unrolling small reinforcement. And we have fiber approaches, where you are integrating fibers in the material. So again, a proposal from TU Dresden that you see MCF process, which pulls actively fibers, long fibers, and our proposal that we call flow-based pultrusion. This involves very small reinforcement with very thin unidirectional strands of multiple small fibers that are embedded into the printed laces, and that allows us to have a composite material. But how does it work? First, we start with a full large-scale concrete 3D printing system provided by X3, which is big components. You add up some accelerator additive inside. The mortar as the input is very flowable, but thanks to the addition of the additive, you have a phase change. You go from really flowable and then it becomes really thick. And we use this phase change to both impregnate and pull the fibers passively without any additional motor. It's just due to the flow of the mortar. You have here an illustration. You have the same system, but with the flow-based pultrusion nozzle added that allows to put the fibers inside. And since the mortar stays relatively flowable, at some point it impregnates and then it thickens, so it can pull the fiber thanks to the flow. Okay, and here's a video of the process. So you see that it's running with the large printer and allows to do quite a large object. For now, this is one of our last prototypes that spans like 2 meters long that I will show you afterwards. And on the left, the right, sorry, you see the carbon roving bundles that are embedded into the multiple laces during the extrusion. So what can we have? So once that we have the reinforced material, is it working or not? So first we did some mechanical tests, just direct tensile tests, sorry. We have 3D printed laces and then we pull them to see how it breaks. If you don't put any reinforcement, it remains elastic and then it breaks in a brittle matter. And that's very normal. And once you have a sufficient volume of fibers embedded, you still have this elastic range that it's not much improved for now. That's kind of the current limitations. But then you enter a ductile behavior, just like reinforced concrete. You have, but then it's a very different mechanics, and you have multi-cracking of your sample. As you see on the image, you have a video of the test where you see the cracks appearing with the color gradient. And at some point, you will have a localized crack opening and the sample will fail, right? But at that point, we have a large improvement of the tensile strength of the material and a ductile failure type, which is good for construction applications. But now what can we do with this? To discuss that, let's just get back to a typical reinforced concrete beam. So you see the concrete beam here. You have longitudinal steel rebars to retain the bending moments. And you have, sometimes you don't have them, but you have the transverse steel rebar for the shear stresses. And the problem is often you have this mandatory reinforcement volume, and that's a problem with the integration of such technique with into thin elements, right? And thanks to anisotropic concrete and other composite technique, you can propose new systems that are inspired by the old heritage of concrete, but also the newer heritage, I would say, of the composite industry. When you are making thinner and lighter components, here you see that we have aligned the laces into in the direction that puts the right reinforcement in the right direction. So we have fibers aligned in front to retain a bending moment, but we can have transversely printed concrete as well. But also, if you discuss with people from the industry, they will say that the problem with that is you don't have enough mass for the acoustics, but you can certainly put mass in another way with filler material, okay? And you need to, let's say, think composite, as the people from composite likes to say when they describe their structures. But you can do many other things. So we've seen already all the nice ribbed components that Pierre-Louis Navier did in the time. We can revisit that. We can also think about trusses, where we have aligned stresses, normal stresses with the rebars. So this prototype isn't reinforced with anisotropic concrete, but it's a first design that we did with a processing system that involves putting supports and then printing laces. And at the very right, we have thin shells. And this is not an arch, it's a shell. And you see that you have some little double curvature, as you see from the profiles. And this is reinforced with the fibers. And that's fine because this shell allows not only to retain distributed stresses, but thanks to the tensile reinforcement, it can also deal with localized loads. And the fibers are aligned in the direction of the main direction of this shell, okay? So thank you very much for your attention. I conclude on that, and thank you.
Thank you, Leo. Do we have any questions from the audience? Yes.
Thanks for the presentation. And you showed us the carbon fiber reinforced printing process. And I'm wondering whether isn't carbon prone to oxidation or some chemical effects with the concrete? Or will it just
you mean
be
the carbon
like
fiber?
Glass fibers?
With the glass fibers, you mean?
And no, you printed with carbon fibers in the video, where it stated
yes,
carbon fiber.
and glass.
So is there
well.
something happening in between the concrete and the carbon fibers on a long term?
We didn't tested this.
Okay.
But what we just know is that carbon fibers are well used in reinforcement for concrete already. And yes, you could also have glasses, but for glasses you can have problems due to the alkaline environment, but there are like treatment for that for the glass. And we are still quite open on the definition of what material should be used for reinforcement here.
Thank you.
I didn't get it. Maybe thank you for the presentation. Just how much did you observe if the fibers go from one layer to the other? Because at the moment, normally, if you print it, you still stay within one layer. So, did you see that there's an overlapping of the fibers a bit throughout the layers or not? I'm not sure if I understood.
I thank you. Thing is that within our process, with 2K process, you are pressing a bit the layers. You are not just depositing the layers, so there might be some, I would say, sagging, and so that would maybe help putting the fibers like moving down, or yes, but from what I've seen, I didn't see so much displacement, right? We are inserting like from 5 to 10 rovings into the laces. This roving, they got impregnated and pulled by the mortar. And then, so inside the printer, they are like in a circular arrangement. And then within the printed laces, it's more like elliptic, but it's not like moving too much.
Thank you, Leo. And thank you everyone for your attention. We will now have a 10-minute breaks before we resume for our last session of the day.